Uh, Good. Just 1 minute. Good evening, everyone. Am I audible to you? And can you see my screen? Just let me know. If you want to speak, you can unmute yourself and you can say, or you can just write in the chat box. Anyone? Yes or no? Kritika? Hello. Kritika, yes, Madala. Can you hear me? And is my screen visual to you? Hello. You can write in the chat box also. Satish, can you just can you confirm? Am I audible to you? And can you see my screen? Why no one is responding? Satish, please let me know if I'm not. You can write in the chat box also. Hello. Why no one is responding? Any problem? Kritika, Satish, Srinivas Rao. Anyone? Please let me know. Hello? 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 Yeah, yeah, I am tech. Yeah, I am in the class. Actually, no one. No, I am in the class. I am asking. There are five people, but no one is responding. I don't know why. Yeah. Sorry. Just 1 minute. Just 1 minute. Oh, sorry. Shit. Just 1 minute. Oh, I was on the wrong ID. Sorry. Sorry. Hello. Can you see my screen right now, everyone? Hello.
Yes, we can see the screen, sir.
Sorry. Thank you for letting me know. And sorry for the some delay.
It's fine, sir.
Just so just 1 minute. Hmm. Good evening, everyone. My name is Maniratnam Prakash. Welcome to the fifth session on wastewater treatment and recycling. Uh, so, the course instructor of this subject is Professor Manoj Kumar Tiwari. If you face any technical problem like sound problem or if you are not able to see the screen, please let me know. I will and I think somebody is on mute on the. Kritika, can you mute yourself? Kritika, please turn off your mic.
Good evening, sir.
Please turn off your mic. I think your mic is on. If you want to say, if anyone have any question, they can write in the chat box or they can just, if you want to speak, you can speak also. Again, I think you have turned on your mic. If you want to say something, yeah, you want. Okay, so welcome to the week fifth of the session. Generally, we meet on every Tuesday, but I will be traveling the next Tuesday at some location. That's why I won't be taking any class on that day. Uh, and recording of this session will be has raised. Yeah, please let me know what do you want. Do you have raised your hand, Kritika? Do you want to ask any? Do you want to ask something? Okay. Hmm. So in week fifth, so till now, if you have gone through, so till now we were trying to understand the basic about wastewater. Your voice is not coming continuously. Just one. Is it for everyone? Everyone, you are not able to. Everyone, are you facing? Rahul, are you also facing this problem that my voice is not coming? Rahul, yes, Srinivas Rao. What about others? See,
We can hear you, sir. We can hear you.
so I think Kritika, I think it's problem from your side. Others are saying they
Sir,
are
we can hear you.
okay. Okay, thank you. We can hear. So I think please check your internet connectivity, Kritika. I think it's problem from your side because I have asked other and they are saying that they can hear me clearly. So what I was saying that till now uh, we were looking what are the wastewater, what are the different parameters that that we should find out that will help us to make a better treatment unit. So in last we read about some CFSTR, PFR and different treatment unit, and I have referred some book. That book is I have also uploaded on the Google Drive, the link for which has been shared with you, so you can always go back and check it. So till now with that now we have some basic knowledge that what is wastewater, what kind of wastewater is generated at different location, and uh, what are the different parameters that we have to measure for our treatment purpose. So now we will be going into the treatment basic treatment plant. That so the thing was the basic municipality wastewater treatment, then wastewater treatment unit. There are different units we will be looking into it, and finally we will be looking into the primary sedimentation thing. So this is the general treatment plan. Okay, if you can go through any book you can go through any book and you will find this that they have this they have layout that what are the different treatment unit. So first thing is that preliminary treatment. So here what we do that we remove all the larger particles, because we know that our sediments, our different unit that is for treatment of wastewater have certain limitation. So the first and foremost thing they want that there should not be any larger particles. So here we do preliminary treatment here. So we know that wastewater is coming from different location, and it will contain larger rocks, boulders, or some unwanted thing which is not suitable for upcoming unit. So we have to remove it. Then we have primary treatment unit. Then we have secondary treatment unit, and then we have advanced treatment unit. Most of the treatment plan are till secondary treatment unit. Okay, now advanced treatment unit we have some specific purpose, like we want to treat our wastewater for drinking purpose or something else, then we go for the advanced treatment. But the most of the location you will see that they will go through the secondary treatment unit, and after that they will discharge into river or any pond or any land. We have different criteria for disposal. Okay, so these things are seen. Okay, so you can take a picture, or you can this is like this is also available in your sorry, the PDF that has been shared on the NPTEL portal. You can always go back and check there. So if we look into the different units, the first is preliminary treatment. It contains a screens and grid chamber to remove larger debris, to remove sand, gravel, and other heavy particles. Then we have primary treatment to allow solid to settle at the bottom. Then we have secondary, that is biological aeration tank, where biological degradation of organic matter. We know that our wastewater contain lots of organic matter, then we have to remove those organic matter. And then finally secondary clarifier to settle the biological mass form in the aeration tank. Okay, so these are the different units. And finally we have tertiary treatment to remove the remaining suspend. So we know that after treatment there will be some suspended particles, then we will have some pathogens, so we have to kill those things. And finally there is another part. So in all the parts there is a sub part, that is sludge treatment. In secondary unit we got some sludge, in primary treatment unit we will get some sludge. Then we have to treat it. The basic process is that so we will be going through through these topics in much detail in upcoming weeks, maybe week 3 or 4 next week, maybe sorry, week 7 8. So we will be looking into these different treatment unit, but for now I am just giving you the brief introduction part, that how this wastewater treatment plant work. So I think this is clear to everyone. So as usual, we will be going through uh, what do we call question and answer. I will be showing some question, and I there are few people here, but I want everyone to participate, and after that we will be discussing the answer. So the first question, that we have to match the treatment stages given in the first column with the target contaminants to be removed in the second column. So given out the basic thing that we have discussed, everyone please participate and try to answer this. Everyone please take your time. It's like very simple question. We have got one answer, that is C. We have got one answer, C. What about other Kritika and Serini? C. C, yes, C is the correct answer. That primary treatment, that we have to remove suspended matters. Then we have secondary unit. Here we have to remove dissolved organic matter, and then we have tertiary unit to remove microbes, TDS, and nutrients. Yes, this is correct. So already, so like we have discussed about primary treatment. Primary treatment, then explanation is also written, that first stage treatment where the physical process like screening and sedimentation are used to remove the larger particle. Then we have secondary treatment. The We have to remove the organic carbon, dissolved organic matters. Organic matter mostly will be in carbon, nitrogen form. So then we have to remove this thing. The stage significantly reduce the biochemical oxygen demand and organic matters, organic pollutants in the wastewater. Okay, and we will be in upcoming weeks we will be also reading how these treatment unit work. Then finally we have tertiary treatment to remove nutrients and microbes. Tertiary treatment is advanced cleaning process that typically follows secondary treatment, and it is designed to remove the remaining inorganic compound nutrients such as nitrogen and phosphorus, microorganism, total dissolved solids. This stage often includes the process like filtration, disinfection, and chemical treatment. I hope this is clear to you. Coming to the second question, which of the given treatment stage is not included in the preliminary treatment of wastewater? Not included.
A.
So oil and greases, just by skimming tanks. Okay, well, I have got one answer, A. What about other? They are asking not part of. I don't know. Just read it. Not included. Not included in the preliminary treatment. So I don't know why you said A. B is the correct answer. Yeah, B is the correct answer. We will look like C. Hmm. So the preliminary treatment of the wastewater is the first step in the treatment process, focusing on removing larger and easily separable contaminant to prevent damages or clogging of the subsequent treatment unit. It typically includes the following: so I think I have not added the part. So first, oil and grease are removed are is a part of so they were asking not included in the preliminary. So this oil and grease are removed in the preliminary treatment, whereas skimming tanks are there to remove oil. So you might have seen, so I don't know, there is a like you if you search that video on if you search on internet the wastewater treatment, they will show you each and every part, like how oil is removed, how suspended. So there is a roller type of thing. They will remove this thing, and there is skimming tank that uh, remove the oil and grease also. So generally, what happens that if the wastewater is coming contain some oil, so the oil will be floating on the those wastewater, because we know that due to density difference it will be laying above the water. So somehow they remove it with the help of a skimming tank. Floating material are removed by screening, which is a part of preliminary treatment. Grit and sands are removed by grit chambers. Grit chamber are used to remove heavy inorganic particles like sand, gravel during preliminary treatment. Secondary treatment involves the removal of finer suspended. So the correct answer is B. Suspended matter are removed by sediment. So sediment. So secondary treatment involves involves the removal of finer suspended matters and everything. Okay. So we will be looking into what is this secondary treatment unit. So before that, coming to the third question. After that, I hope this is clear to the Kritika. You were saying, yeah, you have already said okay, sir. So if anyone have any other doubt, then they can ask, or let's solve the third question. Which of these unit has a detention period of order of 1 minute? Which like water will be staying only for 1 minute at this particular unit. Great chamber, primary sedimentation, sedimentary, secondary sedimentation, aeration tank. Where will the water will be staying for the larger time? One is saying A, one is saying B. B, so primary sedimentation. So you should think also like primary sedimentation includes removal of suspended particles. So do you think that we have large amount of water and all the and it contains large amount of suspended solid? So all the suspended solid will be settled within 1 minute? I don't think so. It take time. You don't have to go into details. Like you can take some water and just keep it. It will contain some suspended particles. Like we know that we cannot just it won't settle on its own. So we have to add some chemical also. So it will take more than 1 minute. So B cannot be the answer. So we will look the correct answer is A, grit chamber. Okay now, so detention period of the grit chamber is around 1 to 5 minutes. Function: grit chambers are designed to remove heavy inorganic particles like sand, gravel, or other small dense particles from the wastewater. The short detention allows these heavier particles to settle while lighter organic matters remain in the suspension. Okay, so I hope this is clear to those who were saying B, primary sedimentation. Here it takes around 2 hours, 1.5 to 2.5 hours. The process allows suspended solid because we add chemical and many things. Then secondary sedimentation, it also took around 2 to 4 hours. The process is designed to remove biological sludge solids that are formed during the secondary treatment. And aeration tank, it's like it providing oxygen to your wastewater. So that some oxidation can happen and this thing. So it usually take 4 to 8 hours. So the correct answer is C. A, sorry, A. I hope this is clear to you. The one who were the Srinivas Rao, you were saying B. I hope this is clear to you. The correct answer will be A. Which of the following could be the appropriate velocity through the screens? This is like information, like when we design our uh, when we design our this thing, our screening, then we have to fix that this much velocity should be there, 0.8 meter per second. B, yeah, B is the correct answer, 0.8 meter per second. So the Appropriate velocity through the screen typically depends upon the specific application and design requirement. Based on the provider strategy, the common accepted velocity is that through the screen are recommended to be around 0.8 meter per second. The value is supported by various engines. So, like we have the purpose is that there will be a screen. So generally, the screen, a screening. So what? How does your screening look like this? Okay, and the water flow from in this direction. Okay, now, and what happened that this also keeps rotating. This is a, so you will find if there is older version, so there is a manual scraping. So in older in older wastewater treatment, what you will see that there will be some something net like a structure what will be passing. But in currently people are using, there will be a belt like a structure, it will contain some stair like arrangement. Okay, so water will be coming, if some debris are there, it will settle down here, it will be settled down here, and they will, it will be, when it will come to this side, it will be getting thrown, it will be collected at some point and water will pass. So this arrangement are made. I hope everyone have seen a screening, how a screen chamber look. So the correct, the self, so also like there is a concept of self cleansing, that a self cleansing velocity is important to prevent sedimentation. Minimum recommendation effective self cleansing is generally 0.3 to 0.8 meter per second. Values that above the help the solid do not settle down. So we also maintain this. So if the velocity is very low, what will happen that suspended solid will start depositing on the bed of the unit and it will clog. So we don't want, we want all the, if the water is moving in this direction, all the suspended particles should also move in this direction. Okay now, so other of unit, it will be very slow suspended, it is very high, also this is very high, you like, if this is very high velocity is going on, there might be chances that the larger particle will keep flowing with this. Similarly, it is very high. Okay, I hope this is was clear to you. Coming to the next question, question number 5, the equalization tank. Answer of this question. We have got one answer D. Question number 5, answer is D, all of the above. Okay, everyone is saying yeah, it's correct. The correct answer is D. Ankylisation tank is a typically storage tank that is so. So I hope everyone understand. So remember so this is, suppose imagine that this is our treatment plant. Water is coming from many location, and remember that we design our so if you have remember this thing, cfstr or pfr anything, you have seen that there will be the flow should be constant. So now water is coming from different location, and this water, the water is coming from here, will have different flow rate, this will have different flow rate, and if entering here it will damage, like it won't damage, like when we design our treatment unit, we have to design for particular flow rate. So what we do that we store all the water in a tank, and from there we allow the water to pass into the upcoming tank, upcoming treatment unit in a at a particular flow rate. So this is what this equalization tank do. It's a type of storage that a tank that that is used in a water treatment to manage the variation of flow and polluted concentration. Its primary role is to provide a buffer that smooth out function in both quantity and quality of the incoming wastewater. So it has different function depending upon the unit, depending on the different option that has been given to wastewater flow can vary significantly throughout the day due to changing. So the water is coming from here and there. Also, the water is like in the morning time when everyone is using bathroom, a huge amount of wastewater will be coming. In the afternoon, the wastewater coming will be very low. So big, so to make sure that our treatment plant receive equal amount at the equal flow rate, we use this thing. This helps maintain a steady and consistent flow rate to downstream process, which is crucial for optimizing the performance and efficiency of this process. Improve so so improve the performance of downstream process. So by stabilizing the flow rate and the load entering the subsequent treatment stage, the equalization tanks help ensure that this process operate under consistent and optimal condition. This can improve the overall efficiency of the treatment system and reduce the risk of process upset and lead to better treatment outcomes. I hope this is clear. So the and last fluctuating concentration. So the concentration of pollutant in the wastewater can fluctuate due to varying source and equalization tank mix in the influent to average out this fluctuation and providing a uniform composition. So suppose one water contain very high amount of BOD, another contain a small amount of BOD. So in the equalization tank, everything will mix and we will get a equilibrium BOD. So that will help us to design our treatment unit. I hope this is clear to you.
Sir, equalization tank, where it is located, sir? It is prior to grid chamber, or means where it is located exactly?
Just 1 minute. This I think I am also not aware, but so. I think just let me check. I think it will be written here. So generally it is after after this thing between preliminary treatment and primary treatment. Okay, now it's also depend upon the design, like how someone has designed. So, but in general, if you search, I have just searched on the internet. So first they remove all the larger particles and boulders from the screening and grip chamber. Then the water will go through the equalization tank. So it is here after this screening. Okay now, so here you will get this equalization tank. I think I have diagram also. Gee, just 1 minute. So here you can see the here you can see this is like our primary treatment unit. So here the floor, so before that we will have equalization tank. Here the water will be coming at uniform flow rate and it will go to this tank. I hope this is clear to you.
Okay, sir.
So the correct answer was D. So now before going to the next question, I want to discuss something about sedimentation. This is a little bit like I will take around 5 to 10 minutes to discuss something about the term and some formula that generally people use, and that and we will be using these formula and to solve some upcoming questions. So in general, sedimentation is the process in which suspended solids are allowed to settle naturally by action of gravity. Okay, now there will be no pressure or nothing, just there is a water and it will settle down, and it's just by the action of gravity. So that is known as sedimentation. Okay, so there are different type of sedimentation. So if you we will be like using different this type, that this is type 1 settling, type 2 settling, type 3 settling. So type 1 settling is like individual particle while settling do not interfere with other particles. So it's like if you take water and if you see that one particle is settling and another particle is settling, it is not interfering with each other. It will be settling on its own. It will settle on its own. So it's not disturbing anyone. So this is known as type 1 settling, type 1 or discrete particle settling. So the most common thing that people generally use is type 1, type 2. If we know, if we come out to, if we talk about the second, it's like top type 2. So enhanced settling involves adding chemicals like coagulants and flocculants to promote the aggregation of settled particles into larger flocks. These larger particles settle more rapidly than the individual small particle, improving the efficiency of settling process. So now imagine that in your water, some larger particle has settles. So now there are smaller particles which they won't settle on its own, but you have added some chemicals that are known as generally coagulants or flocculants. So what will happen that there will be change in chemistry, and these will combine together and they will form a larger particle. And by that, if they have formed the larger particles, they will have some weight, and by the action of gravity they will settle. So that's why it is known as type 2 settling. Okay, then we have another process, that is hindered settling, or type 3 or zone settling. Hindered settling, in which the particle in the group slow each other down as they fall through a liquid, making the process of settling take longer as it would particle were alone. So it's like something is settling. So it's like after seeing some process, it's a particle group particle in a group slow each other. So it's like this is itself clear, like what is this hinder, and name itself suggests that initially you will say that there is a settling, but after some time you will see that the settling has stopped, not stopped, but it has slowed down. Okay na, so that is known as hindered settling. And finally, type 4 is the compression settling, the mechanism of settling of forcing out the water from the solid due to compressive force of solid on the top. So like imagine that in your particles you will have larger particle, and you will have solid particles, a smaller particle, solid, larger particle, solid, a smaller particle. So what will happen that when it will be coming down, it will also it will be also compressing this smaller particle, and overall they will settle as one at the after some time. So this is known as type 4 settling. So each settling happens at different unit we will be looking at. So generally when you like you should know, first you should know the definition. Second thing is you should know where this type of settling happens. Where does this type 1 settling happen, where does type 2 settling happen, where does type 3 settling happen, and where does type 4 settling happens. So type 1 I will be discussing in the upcoming slide, that is it happen in the sedimentation tank. Type 2 happens in the coagulation tank. Type 3 and 4 happens during advanced treatment unit, when we generally doing the organic treatment. Okay now, I have some doubt with 3, but type 4 I am sure that it happens when we do biological treatment. I hope this slide was clear to you. I hope everyone will remember this thing also. Okay, so anyway, like this is very general question that people ask in Viva. And okay, so now I'm coming to the important. So I'm discussing about something called settling velocity. So settling velocity, generally when we will talk about, we are talking about type 1 settling. Okay now, here like I have not written it, but you have to assume that we are talking about, not assume that this is generally for type 1 settling. So here what we have taken, that we have taken one discrete particles. I have not considered other particles. So imagine that there is a particle in your water, so and it is flowing with some velocity. So if it is flowing with some velocity, what will happen that it will have its own weight, that is W. Then it will have some buoyancy force, and as it is following, it will have some drag force due to water in the water. Okay, I hope this is clear to you. So the weight of the particle is will be volume into its density. We know that density is like mass by volume. So the weight of the particle will be volume, and we know that. And one like I have not written the assumption here, but the assumption is that we will be considering the particle as a spherical of uniform weight, and it is not hindered by other the I hope like you can read in book also. Like I'm telling you also, but you can read in the PPT or any book. So the weight will be, and the buoyancy force that acts upon will be again into volume into it, but here it will be density of the water. So this is gamma is known as a specific density of the water and a specific density of solid, and the drag force is given by this formula 1 by 2 cd into density of the water into velocity into area of the particle, projected area. So remember this is a spherical, but if we look into, so now as it is flowing, imagine that this is our surface. Imagine that this is our water surface. So but the drag we have to take if we have a sphere, it will be forming a if we take the projected area, it will be forming one circle on that water surface. So that area you have to take, and that is given by, that will be given by pi r square. CD is the drag coefficient, rho w is the density of the water, ap is the velocity, sorry, projected area, and v is the velocity. I hope this is clear to you. Moving forward, now imagine that so it will start. So we have something in water, so it will start settling. So you will see that it is settling at uniform velocity. So that uniform velocity will be referred as equilibrium. So if we look into the force, we can see that this plus B plus D, that is buoyancy force plus drag force, this upward force will be equivalent to weight. We can write. So now if we want to write in the form of d, so what will happen, that d will be here this side, so it will go, and this b will go on the this side. So the final equation will be fd is equal to w minus fb. Drag force is equal to weight minus buoyancy force. Now if we put all the value, drag force formula we know, the weight we know, and the density we know, sorry, buoyancy force we know. Now we will be taking this 4 by 3 pi r cube common, we will getting gamma s minus gamma w. Now this r and ap we have put as pi r square. So this r square will cancel out, and we will be getting only 4 by 3, and this pi will also get cancel out. Okay, so we will be only getting 4 by 3 r gamma s minus gamma w. Okay, and we know that this gamma w density of the water we can write in the form of a specific weight divided by g. This is, I think, everyone know. And this sorry, and this radius can be written as d by 2. Okay, so we will be putting this value here. So if we put this value to here, 1 by c gamma w by g v square by 2 into 4 by 3 d by 2, and we know that gamma s by gamma w is known as gs. That is a specific. What is gs? Can anyone say what is gs? What is gs? Can you write in the inside? What is gs? Anyone? specific gravity, huh? That is a specific gravity of the solid. You are right. So now imagine that this we have converted this thing here. So a specific gravity of solid. First, let me tell me. Are you understanding the proof? I'm deriving the settling velocity formula. I'm sorry, deriving settling velocity formula. So, are you understanding what I'm saying? Let me know in the chat box. Yes or no? Kritika, Rahul, Srinivas Rao. Yes. Okay. Huh. So now what I will do that this. Mhm. Hmm. So now what we have done that we have taken out this gamma w on this side. Okay. So here we have taken this gamma w. So this will be converting into one. This will be converting into one, and this gamma s by gamma w we can write as gs. And we have also we know that this the at the velocity at which it is coming down will be as settling velocity, that is vs. Okay, vs. So now we have put down each value. So if now what will happen that we will take out g this side, we will be taking cd at this at the bottom, then finally settling velocity formula which we will be getting as 4 by 3 into g into d into gs minus 1 by cd. Okay, so this is like a general formula. Everyone can, so can you like if you are appearing for any like in if you are in your btech or somewhere, this derivation will be asked to you. And if you are appearing for some written examination at there also they will ask this derivation. They can ask, anyone can ask. Okay, so now we know that this vs is equal to 4 by 3 into gd into gs minus 1. Okay, so now there is concept of like at what, so something is like we know that there can be the water which is at which the settling, the flow can be of very different type. That is, it can be of laminar flow, it can be very fast flow, then that is known as transient flow, and then we have turbulent flow. So depending upon the type we have something called Reynolds number. Okay, RE is defined as density into Vs into diameter of the particle divided by dynamic viscosity. Okay, and similar to dynamic viscosity we have kinematic viscosity, and that is generally referred as mu by density. Okay, so as when the condition is laminar flow, suppose in your system it is saying that so thing is that we have this drag coefficient depend upon this type of flow. Okay now, so what happened that you will be given some velocity and you will be given some density. You will be not you won't be given the velocity you will calculate using this formula. Now you will put, so actually let me tell you let me drive first, then I will tell you why it is important. Just remember this, the formula of cd depends upon the type of flow. And as suppose if your flow is laminar flow, then cd is defined as 24 by Reynolds number. And we know that re is equal to rho vs by d into mu, or rho mu this. So this is mu, and I don't know what is it is called, but it is like you can either represent in the dynamic viscosity or you can represent in the kinematic viscosity. Okay, so what will happen that we will be putting this value this cd here. Okay, we can put 24 vs by d here, we can put or not. So if you put it and if you derive it, you will get the vs is equal to gd square into gs minus 1. So you don't have to memorize it, but you should know that you should know how to derive it. If you are preparing for gate examination, you should memorize this formula, that when the condition is laminar flow, the viscosity formula is gd square into gs minus 1 divided by 18 into kinematic viscosity. I think it is new. I don't know. It is mu. It is new. Maybe. Okay. Is this clear to you? So this was laminar flow. I hope this is clear to you. Now, when that so this was like laminar flow when the Reynolds number is less than one. But now imagine that your transient flow and if you found that laminar flow is the Reynolds number is greater than equal to one or less than 1,000, then you have to use this formula. This little bit wrong dirtier formula, that is known as 24 by RE plus 3 by under root RE plus 0.34, that is roughly equivalent to 18.5 into 18.5 divided by RE की power 0.6. So if you find out the Reynolds number is this much, then you have to put this value here. Okay, and then you have to find Vs. If you like, there is no derivation like for laminar flow. This we got this type of equation because this was simple, but for this case this CD, this is not very simple, so it will be very complex. So there won't be any derivation for Vs, but you should know that if your Reynolds number is between this, then you have to use this CD and you have to put here, and then you have to find Vs. I hope this is clear to you. And finally there is something called turbulent flow, but which I have not written here. What's Reynolds number? So Reynolds number helps us to define what is the limit. So so Reynolds number is like a formula that is given us to identify the type of flow. Laminar flow is like when the water is flowing very smoothly. Okay, very smoothly. And transient flow is like water is not flowing smoothly, but it has very high velocity. And there is a third turbulent flow, very turbulent, so water is flowing with some turbulent. So this Reynolds number help us to identify the type of flow, and the formula for it is this: density into Vs divided by mu into dynamic viscosity. Or you can use this formula also, like viscosity, sorry, velocity into diameter divided by kinematic viscosity. I hope this is clear to you. So if someone asks what is, so Reynolds number is used to identify the type of flow given by this. Am I clear to you? Hmm.
Yes, sir.
Thank you. So finally we know that settling velocity, this is general settling velocity, and depending upon the type of depending upon the Reynolds number, you can identify the laminar flow or turbulent flow, and depending upon that you have to use this. So this is for type 1. Remember, generally in our sedimentation track we have type 1 velocity, type 1 settling, and for type 1 we use this formula. I hope this why like here, like when we were deriving it, we assume that there is a single particles dropping, and this is the definition of type 1 also. So when we will be talking about settling velocity in sedimentation tank, we will be using this formula. Am I clear? And just like settling velocity, there is a scoring velocity also, scoring velocity, that is Vs, that is given by, and this is like we know that when water is flowing, there will be some particles flowing along with it. So we don't want that particles to settle down. Sorry, sorry, not particles. So it's like if something is laying, how to define scoring, just 1 minute. It's like, this will be used in sedimentation tank. Okay na. So now when this formula is used when the water is flowing through any particular unit. And because we know that I want our settling our so I so I was talking na, so ki like when water will be flowing, I don't want our sediments to settle anywhere else. We want our sediment to settle in the sedimentation tank only. So that's why there should be some minimum velocity. So that velocity will is given by this scoring velocity, that is 4 under root g. I hope this is clear to you. This will this also help us to define our self cleansing velocity, and it is generally between zero point 0.8 that you have I was so there was one question ki what should be the minimum velocity. 0.8 meter per second we discuss. So this velocity was determined by using that um, by using what do I called that formula only. So this help us this formula help us to make sure that the whatever is suspended particle is there, it keeps moving and it only settle at its designated place. So generally if you solve any question, this value will be given to you. But in general, for particular, so this g is taken as 2.65 capital G, that is a specific density of the particle. Then gravity is 9 point due to acceleration is 9.8, that is rho p or rho w, that is from here we can identify. And the viscosity, this remember, this is dynamic viscosity, sorry, kinematic viscosity. Always do not get confused. uh, huh. So this is dynamic viscosity and kinematic viscosity, both will have different unit. So hmm, remember the unit of this viscosity is 1.01. So I think I think in 2021 when I was appearing in the GATE examination, they have asked the unit of, I don't know, in GATE or somewhere, but I was appearing in one examination and they have asked this unit of this kinematic viscosity or dynamic viscosity, but they have asked. So everyone, please make sure that you know the unit. If somebody is appearing for GATE or JAM, this kind of question generally asked. And so I hope this is clear to you. Any doubt here? Whatever derivation, I hope I have tried my best to explain in a very like simple way, and I hope you have understood it. If anyone have any doubt,
So,
huh?
what sort of questions? October 18th, there is an online exam, sir. What sort of questions they will? It will be coming.
So every year the practice is that they will ask a similar type of question that they ask in your assignment. There will be what do I call, theoretical question around. There will be some theoretical question and there will be some numerical question. And the theoretical question you will have multiple choice question or single choice question, and in numerical question generally they have you have to fill something there will be some sets of question for there will be one single 2 3 liner question, and then you have to answer 4 5 question depending upon the given information.
So, if we follow the every week, whatever the questionnaires which we are receiving, it will be enough, sir, or
No, it won't.
anything more?
I think, see, if you want to, it will be enough just to get a minimum score. But if you want to perform well, refer to the books that has been. If you want to perform really well and if you want to score really high, then I think you should practice more. And you can use any standard book available on internet or in your library or anywhere to get this kind of question. So if you just want to pass the examination or like get a certificate, then that will be sufficient. But I think there is a criterion that if you score between this, you will get this kind of certificate. If you score above that, you will get that kind of certificate. For that, I will suggest that go through some book, study it, try to solve those questions.
Can you recommend any book, sir? Any such book?
Uh, for just 1 minute. Mm, Currently, I'm not able to recall. So there are some few books of Indian authors. You might have also gone heard of S.K. Garg, Wastewater by S.K. Garg. So it contains lots of practice question. Huh. Wastewater, like this waste sewage disposal, wastewater treatment. So it contains lots of numerical question. Okay, now, and in general, if you want to read about uh, if you want to read about theoretical concept of these things, for theoretical uh, for theoretical concept, you can go through. I hope everyone have link of everyone got this link where we have this what do I call
Yes, sir. We have this link, sir.
so here if you like I have if you go through the big four of my folder. Why it's not opening? Just 1 minute. For practice for practice purpose, you can go through that book, and I'm also showing you two more books. uh, that you I have uploaded the PDF of that book in my this the I don't know why you. Oh, somehow my laptop has gotten bad. I don't know what's happening from last 2 days. Hmm. So yeah, here you can also refer to this chemistry. So here this is kind of theoretical. So theoretical, like it does not talk about treatment and everything, but it talked about where can we find just, but talks about different terms BOD, COD, and everything. So you can also you can read these book also. Uh, but let me tell you, this is not directly related to your wastewater treatment. Till big four, this book might be useful for you. We talk about DO, BOD, COD, then pH and everything. Then we have some discussion about kinetics. Yeah. So if you have attended big four lecture, or if you have gone through the big four session, then they were talking about CSTR, PFR. Do you recall this thing? I hope you recall. For that, you can go to this book, this surface water quality modeling, and I think they were talking about advection, dispersion, and this DO curve equation, DO curve. So for that, you can refer to this book. Where can I find so this link is generally shared with you. If you don't have that link, then I am just sharing. You can just you can open it. I'm just you can. I think this is shared with you on through mail to. I think it's in your NPTL portal also. But for now, you can use. I have shared you the link. You can use that all the this link also. I hope this miss I will try to get you some more books. Maybe if you attend next week, so next week will be in September, I think. 2nd September, yeah, 3rd September, I don't know. So I will try to get more of book, but as of now, consider these three books. And best way to practice this wastewater treatment, if you want to just practice questions, you don't want to go through a theory, just go through the previous year question of gate. And specifically there is a different particular section of environment, so you will find wastewater treatment. So there you will find many questions related to wastewater treatment and everything. So these are the four reference which I would suggest.
Thank you, sir. Thank you.
I hope this was clear to you. If it is clear to you, please and everyone answer question number 6. Everyone answer question number 6. For real settling basing, the assumption of ideal discrete settling may not hold true. Real settling basin usually have fluent or type 2 sedimentation. What is type 2 sedimentation first? I missed it. You are saying that statement 1 is incorrect. Why statement in 1 is assumption of. So if you see the real settling basin, so if you see the real settling tank, they talk that first of all in ideal discrete particle is like they said that one particle won't interfere other. This will settle independently. This will settle independently. Imagine you go to any wastewater. If you take 1 cup of water, do you think the particle which will be settling independent of each other? I don't think so. But for our convenience, for our derivation purpose, I think I have told you the assumption that this thing we assume that it won't interfere in type 1. So these are just assumptions. So that might not be true. When so like we have to design something, and for designing purpose we have to assume something, and we will be assuming that is convenient to us. So if we talk in that sense, uh, we can derive, because these are just mathematics, but in reality does that happen that if one particle is settling, it will settle on its own, it won't be disturbed by other? No, it does not happen. It is always so. Statement 1 is correct. For real settling basing, the assumption of ideal may not hold true, but for derivation purpose and for calculation purpose we assume it. Real settling tank may so real like it's like type 2 sedimentation. Type 2 means like a smaller will be grouping and will be forming. So so this is the reality. So I think both statement are correct. So the answer will be C. Though so if you are saying B, I don't know on what basis you are saying B, but just try to think that Type 1 is just an ideal condition which does not occur. It's occur in other field, but in our wastewater it does not occur. For assumption, in idealized settling to the particle are assumed to settle individually without interaction with other particle or influence from the basin condition. However, in reality, basin these assumptions do not hold. Factors such as particle size, distribution, particle interaction, and non-ideal behavior flow patterns can affect the actual settling behavior. Therefore, the real world condition often lead to deviation from the ideal discrete particle settling model. This is what I was explaining, that others one particle will be hindered by other particles, so that might not. So that's why statement one is correct. Second statement is real settling basin usually have type 2 sedimentation. In practical matters, many settling basin ideally deal with the type 2 sedimentation where particles tend to form or aggregates that settle together rather than individually. Type 2. So this is also what I was discussing few minutes ago. So type 2 sedimentation occur when the particles interact and form larger blocks which settle at different rates compared to the usual particles. This is common in real system where wastewater often contains a mixture of different particles and flocks. So that's why the correct answer is, thus both the statements are correct. The correct answer is but C. Am I clear to you? Okay, thank you. I forget to mention one thing. I forget to mention one thing. So generally they will ask you to find out the settling velocity. And in your question you will see that these information will be given to you. Okay na? So now you will be using this. Suppose you have used this formula. Okay na? Now just listen carefully. If you do not understand, please let me know. Because I am going to tell you something important. So they will give you this information. G is this capital G, small g, and then viscosity, everything will be given to you. Then you will be asked to find out the settling velocity. So what you will do, you will just simply put and density will be also given to you. Sorry, diameter will be given to you, diameter of the particle. So you will find out settling velocity. Now what you have assumed, that if you have used this formula, you have assumed that your flow was laminar flow. Okay, so whatever Vs you have got, you have to put it. Huh, huh. So what will happen, that using those value you will find out Vs. So now you will put Vs here. You have already density for value, viscosity value, and diameter velocity. You will put the value D, and you will calculate Re. Okay, if you if your calculated Vs give Re less than 1, then you will, whatever the Vs that you have got from this formula is correct, you can report that answer. But imagine that it is coming greater than 1, then you won't report that Vs. You will be calculating new Re from, you will be calculating new Re by here. Because what has happened, your this thing your because this formula holds for um, laminar flow. But as you have used this formula but you have not got Re is equal to, then that is not Vs. Whatever Vs you have got, that is not correct value. So now you have to put Vs here. Now you have to use this, sorry, not you have to put, not you have not you don't have to put Vs. Now you have to use this, you have to put Cd, that is R 18.85.0 R6 here in this formula. Then you have to calculate new Vs, and again you have to recheck that by putting whatever Vs that you have got here, that is making sure that RE is between 1 to 100,000 or not. If it is yes, then you will be saying that yes, this Vs that I have got is corresponding to the transition flow for that particular particles. Am I clear to you? Did you everyone? There are four people. Did all of you got this thing that I am sharing with you? Yeah, that just I explained with you. Whatever Vs you have got using this formula, then see, you cannot use this formula directly because you don't know CD. So either you have to use this formula or you have to use CD here by putting here. So generally this is the most common formula that everyone remember. So you will be calculating Vs, then you will be calculating Re, then after calculating Re you will check whether it is laminar flow or not. If it is laminar flow, then that Vs is correct little bit. So I don't know whether I have question or not, but I will try to get some. I will show you so something, okay, at the end of the session. But I hope others just hold on for few minutes. I think I have some question. We will solve it, and then I think you will understand what I was saying. I think others have understood. Now coming to the question number 7, settling velocity under flocculent settling is. Just answer this question. It will be higher than lower than discrete settling. We know that Vs is discrete settling. So that is due to like that is settling at its due to gravity. All the settling is due to gravity only, but it will be higher than the discrete settling because here we are using chemicals. So whatever small particles have been there, they have form a larger one. So can you say this will be large, its velocity will be larger, it will be same as this velocity or that single particle, or it will be higher than discrete settling, or it will be lower than the discrete settling. Very simple. Anyone? Higher, lower, same, or could be anything. C, higher than the discrete settling. Yes, correct answer is C. uh, Higher than the in flocculent settling, the particles form flocks that typically have a higher settling velocity than their individual discrete particles. This is because increased mass, faster settling rate. So under flocculent settling, the settling velocity is generally higher than the discrete particle settling or type 1 settling. I hope this is clear to you. Those who hasn't answered it, I hope this was clear to you. Hmm. Now coming to the question number 8. Yes, sir. The zone located at the bottom of rectangular sedimentation basin is. So this you will be able to answer only if you have gone through the sedimentation tank figure or you have gone through the lecture. Sludge zone. Yes. So here you can see that at the bottom we have sludge zone. Inlet is here, outlet is here, settling zone is in the middle. At the bottom we have sludge zone. So the correct answer is, oh, why did you say C? Settling zone will be in the middle. this is the most important part of sedimentation tank. Why did you say C? All the particles that will settle here, it will form. So this complete zone is known as sludge zone. This I'm not drawn it correctly, but this complete zone will be known as sludge. And all the sludge are passing through here, and so this is sludge zone. It does not need any explanation. That's why I have not put any explanation. Just I have added one picture, and everyone should know how to draw this sedimentation tank. If you like, your this here NPTL will be mostly what do I call computer based. But if you are appearing for any written examination, so just one out of context question: what you guys are doing? Are you a student or are you working somewhere? Srinivas Rao, are you a student or what?
No, sir. I'm working, sir. Actually, my whole I'm a basically civil engineer, but my whole experience in building. Recently, we got one new project, wastewater treatment plant. So, to understand the wastewater treatment plant, I enrolled this class, sir.
Okay, and you are from which company?
China State Construction Company. It is a Chinese government company, and we got wastewater treatment project in Kuwait. It's per day 500,000 cubic meter per day capacity. It's a huge project. It's a huge project. We got it. So we are going to execute. Now we are in design period. You can say 13 months around the design period. Then after that we have a construction 4 years. Then operation and maintenance 5 year. So total it is a 10 years project.
Okay, got it. So like, so you are currently from you are attending from Kuwait.
Yes, I am attending from Kuwait.
So I think I will share you one thing with you. Just there are three people only, so it's like our notes from like the content are same, but you can go through the lecture notes that when I was doing this course at IIT Kanpur, I hope I had those. So like just one thing, don't share that with anyone 412.
No, sir, we will not share.
Like it's the lecture, I don't think anyone attend just 1 minute, let me delete this thing. So this is 412. It's like design of water treatment and waste disposal system. It contains two part. So I think from week 1 to week 7 it will be water treatment, and after that it will be wastewater treatment. So this is class notes of one of the professor from IIT Kanpur, Purnendu Bose. You can search about him. He is a really good professor, and go through the lecture notes of it will be like, see, the content wise it will be same, but I can give you that it will be little bit extra than what you guys are studying here. So I am sharing
Thank you, sir.
with you. So these are just for you guys. Just download everything and you will be able to. And if you have, and it contains some questions also, okay now. But that questions I won't think that will be relevant to your this NPTL. These are little bit on the higher side, okay now. So I want to like, if you want to practice on your own, you can practice, but let me tell you, it won't be because the type of question which will be asked to you at NPTL will be much easier than what has been asked here. Okay, what about Rahul Kumar? What are you doing? Hello, are you a student or you are also working somewhere?
A student, sir.
Oh, from where?
Patna, Bihar.
Oh, oh, okay. And what about Kritika Ojha?
Sir, I'm an aspirant assistant state PCS, sorry, and I'm preparing for sanitary waste management exam. So there's a one unit of wastewater treatment.
Oh, you are also from Bihar.
No, Jharkhand.
Okay. This sanitary examination happened like what? Was this cancelled or what?
Yes, sir. Sir, it was last 3 years ago. One exam is they have taken. They have recruited some that time, and before in April something, I think they have taken exam, but this exam is got cancelled because of paper is leaked. I have attained that exam also. I have scored good marks in that, but
Okay.
that exam is cancelled because of leak.
Yeah, I have also heard about that. Okay, no problem. Okay, all the best for your examination.
Thank you, sir.
Okay, so now, now coming to the question number 9. Everyone, please try to answer it. A. Lesser area but higher energy input. No. So, so this is directly from your slide. This question was directly from your slide. So, here the area is decreased. So, I think here you can see the third point. These are compact unit and therefore usually required only 65 to 80% of the area of the conventional clarifier, and also the energy inputs are lower due to absence of mechanical or moving parts. So, so the correct answer will be D, lesser area and lower input energy. There is another problem with this thing, that like clogging and other thing, but if we talk about area and input energy, uh, it will be lower. I hope this is now moving forward to the there is one numerical question. So first let me know how many of you know about surface loading rate. What is the formula of surface loading rate? If you know, try to solve it. If you don't know, we will be solving it. Take your time. If you know the surface loading rate, just try to solve it. Else, if you don't know, just let me know also. We will be moving forward. pressure. Okay. So remember this surface loading rate is defined. This is the final formula. Okay, na. This is sorry. This is final surface loading rate is flow into divided by length into breadth of the. So this was our sedimentation tank. This will have length and this depth. Okay, na. And there is a width also. Okay, na. So it will be like this thing. If we talk in the, if we look into the 3D, it will be looking something like that. Not good picture. It will be, yeah, 72 second. It's asking about loading rate. So loading rate will be, won't be in second. It will be like meter per something. Yeah, 50 is the correct answer. But what is the, so remember, when if you are regular to my class, I always ask to write unit 50 watt. So remember, just remember the picture that I was showing you to the sedimentation tag. So there we have detention time, which is known as the average time for which water stay in tank, and that is given by V by Q, where V is the volume of tank and Q is the flow rate. And the surface overflow rate, or SLR, yeah, loading rate, overflow rate, or loading rate, you can say, that is given by Q by AS, and A is the surface area of the tank. Okay, so for rectangular tank of length L, width B, and D depth, SLR will be given by Q divided by L into B. Okay, now. So I hope this is clear to you. And if from using this formula, you can also find out the detention time V by Q. V is equal to L into B into D divided by Q. Okay. What I have written here, D by Vs. What is D by Vs? Oh, huh. So, like, there is one thing which generally people say, that detention time does not depend upon length and width of the. So there is one normal question, that detention time in sedimentation tank just only depend upon the depth. It does not depend upon the length and width. So you can just put. So this is the. How can you like derive it? Can are you getting first? Just tell me. I have not written it in a correct sequence, but can you just can you just figure out what I have written? Detention is equal to V by Q. Hmm? Can anyone? Apparently, I'm not able to share a screen on. Are you able to figure out what I have written here? Okay. So just I will try to write here. So, so this, we know that. Just 1 minute. listen. There is no problem in audio and everything. Hmm. So we know that volume is will be given by L into B into D. Okay, and this Q. What is Q? Q is the uh, just 1 minute. Hmm. This Q will be settling velocity into, you know, the area into velocity is known as this Q. L into B. L into B. What is L into B? L into B is area. So now we know that detention time is, what is detention time? Detention time is equal to V upon Q. V upon Q. So now if we put V here, what was the V? V was L B D. And what is Q? Q is Vs into LB. So this LB will get cancelled out. We will have only detention time. This detention time is equal to D by Vs. This thing which we have written. Okay. So from here Vs. So actually it should have been written by this by here. But I hope this you have got. That's why it is said that detention time in a sedimentation tank depends upon the depth of the tank, not length and the breadth. Remember, this is the important thing. If you are preparing for examination on or anything, people ask what is the relationship between the detention time and its length and breadth. But still, so like someone can ask that it does not depend upon length, and so can we make a very longer detention time? So for that we have some other parameter, okay, to determine what should be the length and what should be the width. I hope this is clear to you. So flow rate was 900 meter cube per hour. Surface area is equal to length into width. So 910 meter into 1.8 meter, that is 18 meter. Surface area 900 divided by 18. So this is the unit. Rahul Kumar, you have written 50. That was correct, but you should write unit also. Meter cube per hour per meter square. So the correct SOR is 50 meter cube per hour per meter square. Okay. I hope this is clear to you. Any doubt? Anyone? Hello. What you have written? Meter cube. No. Remember, you do. So here the, if you write meter per hour, it will convert into another thing. Meter per hour is the unit of velocity. They are asking about loading rate. So you have to write that flow. So you should. Sorry, I did not explain. But this has a significance. You cannot just cut out meter square, you should like it is just representing how much flow is coming particular unit, in the particular unit of area. So that's why it is written in this manner, meter cube per hour per meter square. So don't write this thing meter per hour. I hope this is clear to you. Also important thing. Question number 11. Surface loading rate is this thing. Approximately what percentage of particles that have settled will have a velocity 0. Again, I think if you have gone through the lecture, this was discussed, but we will be, we have only 20 minutes. I think there are few things are left, so I will be going. Okay. So remember the formula which is given as particle of the percentage of the particle settled is settling velocity divided by surface loading rate. Okay, now we have surface loading rate how much? 18 meter cube per hour per meter square into 1000. This is the percentage of particles removed. Okay, na? Remember this formula. So now surface loading rate is uh, uh, so settling velocity, it is already given as 0.006 meter square. So now see, I have converted here into, so here now you can ask me that in last question you have said that do not write in this meter per second, but here I have to compare SLR with something. That's why I have converted this unit into meter per second. So if you convert 18 meter cube per hour per meter square into meter per second, it will be coming out to be 0.005 meter per second. So the percentage of particle will be around, it will be coming around 100 to 120%. Since the calculated exceed the 100%, it means all the particle with the settling velocity 0.006 meter per second or higher will completely removed. Thus the correct answer is 100%. Did you get it? So see, surface loading rate is just representing at what flow rate on a particular so this was my sedimentation time, and it is saying that it is just showing that at what speed a particular particle will settle. And now we know that from settling velocity formula that each particle have certain velocity, and if that velocity is there, it will definitely flow. Okay, now so now imagine that settling velocity is 0.06 meter per second, and the velocity which we are providing is like 0.005 meter per second. So that's why this percentage is coming uh, like how much part is coming greater than 100%. That's why we are saying that everything which is there will settle. I hope this is clear to you. I want everyone to solve the next question. I have derived it. If you have gone through the formula, if you have not taken not down the formula, then that is another thing. But please solve it. Take four. I think first of all, let me know. Are you solving? So I won't waste time. We have only 15 minutes, so I won't be wasting. Like I won't be not wasting. I won't stop. I will keep teaching. So tell me, like, are you solving it or not? If I won't get any response, I will keep continue with the solution. D, trying to solve. Okay, just okay. Trying to solve. Then take your time. D means 0.09. So I hope you have done that. So I have said you to check it whether whatever VS you have got is corresponding to the assumption that you have made. So if you have applied the formula GS minus 1 divided by 18 mu into something something, then you have assumed that your flow is laminar flow. So if you have used that formula, if you have used that assumption, make sure that you are calculating your RE, and you should make sure that your RE is less than 1. Okay, so I will move forward. Okay, na. So I hope you will solve it. D. D is the correct. D 0.09. D is the correct answer. So we know that terminal velocity is given that. So for this question, we will assume that we have laminar flow. So see, I'm teaching when I'm doing this thing. I'm assuming that everyone is writing, giving written exam and all. But if you are doing for gate examination, you don't have to write in detail and all this thing. Okay, then. So this is rho vs upon this. So if we keep this value, then we will be getting vs as this thing. Okay, now we have been given. We know that I think in question density of the water is given as 998 kg per meter cube. G we know that 9.8. Then diameter we have been given. What was the diameter? Diameter was 0.01 mm per second. Remember, I have written unit of each and everything. This thing I ask everyone to practice, that whenever you do calculate, write your unit, and then gs, that is gs is unitless, that is 2.65 minus 18 mu. Now the unit which was given to us was it was newton s per meter square. Okay, na. Newton s per meter square. So you can convert that. So we know that this newton is what? This is newton is force. And what is the force? Force is mass into uh, what is force? What is Newton? Newton is kg into mass into acceleration, that is kg into meter per second square. Okay, so if you put instead of Newton, you can write kilo meter per second square. So what will happen that this s will also get cancelled and you will get single s. So the final unit will be kg meter. Sorry, there won't be meter. Kg divided by ms, and kg divided by s. So remember, this is the unit of dynamic viscosity. You should also already written it is dynamic viscosity. So the final unit will be kg ms. So that's that which is I have written here, kg ms. I have put all the value and I have calculated ms at 0.009 meter per second, and if we convert it to centimeter, it will be 0.0889 meter per second. So now I have assumed that it was laminar flow, so I have calculated re. Okay, so that's why I have written that as Reynolds number is greater than, oh sorry, lower than 1. Sorry, I should have written lower than 1. I hope, just let me correct it. Hmm. This one is lower than, hence our correction, our assumption was correct. The final answer is Vs is equal to settling velocity 0.09 meter per second. Okay, so now imagine that it's like this is what I was explaining. You said, Kritika, you said na little bit. That when I was explaining, you said that I understand little bit. So this was what I was explaining, that whenever you calculate Vs using this formula, you should check it. If suppose imagine that this Re was, suppose instead of this you got Re is equal to 8, then you won't reporting your answer as Vs is equal to 0.09 centimeter. You have to recalculate it using transient flow formula. I hope this is clear to you right now. Okay. Now coming to the question number 13. Yes, sir. Question number 13. A circular primary clarifier is designed to overflow rate of 40 meter per day to treat itna meter cube of earth. The approximate diameter. This is very easy question. This is overflow rate or surface SRL only. They have written unit as 40 meter per day, but it like see not depending upon the like I said that you don't have to write meter per hour, but some books use it. Go through the recorded. You can go through the recorded lecture will be uploaded on this the link this link which I have shared. Okay, so try to solve with this question. We know that surface flow rate is given by flow rate divided by surface area. If it is circular, then what will the surface area? Pi r square. So I think we have only 8 minutes, so I will be going through. So the flow rate is 5,000 meter cube per day. Our flow rate is 40 meter and surface area is pi d by 2 uh, this thing. Huh. So surface flow rate will come to this area will be pi d square by 4 here and if you put d diameter you will be getting as 12.62. The correct answer was what was the correct answer? Someone said D. Oh no, sorry. Oh A. A is the correct answer. 12.62 meter. I hope this is clear to you. Again, question number 14. The head loss through a bar rake of approach velocity and the velocity through the screen is 1.05 meter will be. We have to. So again, this is if you know the formula, you will be able to solve in 2 minutes. Oh, sorry, 30 seconds. If you know the, do you know the head loss formula through a screen chamber? Anyone? If not, so this is so here we know that this is the incoming velocity, this is outgoing velocity, so there is a head loss. So head loss is given by k divided by 2g outgoing velocity minus incoming velocity, and generally k by 2g is given by this value 0.0729. So these are theoretical value. You should remember it if you are wastewater like if you are expert in wastewater. Okay, so I will be putting this value here and the final answer will be head loss will be coming out to be 45 mm. So the correct answer would be B. Was this clear to you? So this was all based on your formula. I hope this is clear to you. Now coming to the uh, last question of the day, that a grid chamber with a detention time of 40 seconds is treating a wastewater flow with a flow through velocity of 0.3 meter per second. You have to find out the length of the velocity. Sorry, grid chamber. Very easy question. Very easy question. What would be the length of the grid chamber? This is the most screen chamber and these are the most simple 12 meter. Yes, sir. This was direct flow. It does not for the finding length you don't have to think about this flow rate and everything. So the to determine length of the chamber is whatever the flow through velocity and whatever like so this is imagine that this is our grid chamber. So what? So detention time. So what this grid chamber will do? So water will be flowing out. All the larger particle will settle here. So whatever be the flow rate, sorry, whatever will be the flow through velocity and whatever time it is taking, you have to just multiply it and that will give you the length. So flow through velocity into detention time 40 seconds, 0.3 second. If you put all the things, you will get as 12 meters. So the length of this chamber will be 12 meter. Okay. So there are more questions, but I don't think I have time to discuss it. But these PPT are available on that link. So there are more 12 questions with around 5 6 numerical question. You can go, and I think there will be some repetitive question also, like this thing. This one is repetitive question. So you can go through these. You can go through that and you can try to solve it. You will have more understanding, and if you have any question you can, oh, this time I have not put my LinkedIn profile, no problem, let me check. So that's, if you have any doubt you can ask right now. Or if you want to contact me you can use my email id. This is my email id. This is my email id. This is my LinkedIn account. You can connect me on LinkedIn, and you can also mail me. If you are mailing, make sure to write NPTL. Then you will, there are chances that you will get quick reply. So I hope I have covered everything. Anyone have any doubt? Go through the lectures which I have shared with you. Sorry, go through the IIT lecture which I have shared with you. But remember, if you are preparing for examination like Ritika, Rahul, don't go as of now. If you want to understand in a better way, then you are always welcome to go through. But for Srinivas Rao, I think that lecture notes, if you are particularly looking into the basic understanding of the wastewater treatment, you should go through that lecture. That will be helpful to you. But for others, focus on your examination. Go through. I think for you the most important thing will be your what do I call, gate, previous year gate. So that's
Thank you,
all.
sir.
That's all for today. So if you like, there on week, for week 6, you know that there is 2 TA. So next Friday you can attend that other TA, or I will be meeting on week 6 on 2nd of November, September. So you can join me. If you have any doubt you can ask me. But for now I am ending the session. Thank you all for joining. Tata.